Hello, I'm Edwin Dauber, and today I'm talking about supervised authorship segmentation of open source code projects. This is joint work with my co-authors Robert Erpunker, Gregory Shearer, Michael Weissman, and Frederica Nelson from the United States Army Research Lab, and Rachel Greenstott from NYU. I'd like to give a shout out to Michael Weissman for work on the graphics in these slides. So this work is looking at code attribution, identifying authors of pieces of code. It's often easier to think about this in terms of natural language text. So for this slide, let's consider the text here on the left. Our goals when doing this work would typically be to identify bad actors, such as malware authors, cyber terrorists, and people involved in cyber warfare. It may also include settling legal disputes, such as copyright issues or non-compete. So if we look at this text, maybe there is some part that was plagiarized, or maybe some part of it is malicious, or is somehow involved in terrorist activity. We'd want to identify which those pieces are, and then who wrote those pieces of the text. So in this work, we're translating those ideas into code. But if we can do that, there's some privacy issues that come about that we need to think about. If we can identify cyber terrorists or people involved in cyber warfare or malware authors, we can identify open source contributors or activists, hacktivists, and just ordinary everyday programmers. So we want to be able to understand what these techniques can do in order to understand how much of a threat these kinds of people face. So there's a large body of work that's very successful at attributing projects that are written by a single person. But in the wild, code projects may have many programmers. Now, if these projects are under version control and we have access to the repository, we have a commit history that can give us segments. And then we can use techniques developed in work I presented at PETS a few years ago, don't blame who, in order to attribute those segments. But if we don't have the repository, then we need to segment it ourselves. Now, at this point, some of you may be thinking back to last year to a paper called Multi-Chi that was published last year and did sliding window segmentation of files from 9 major GitHub projects and achieved high accuracy on a fairly large suspect set, which might lead you to thinking this is already a solved problem. But consider that sometimes the changes made to a text that can drastically change its function can be small and can be distributed throughout the code. If that's true, it may be difficult to detect with the sliding window, and even if we detect it, we may be losing information from other parts of the code. But it might be possible to detect these things from the AST, the abstract syntax tree. In which case, we want to try to segment the abstract syntax tree. For anyone who needs a refresher, the abstract syntax tree is how we parse code. Program execution is a depth-first reading of the abstract syntax tree. Right. Individual nodes in the tree may be individual tokens from the code. They may be compound elements of code. The details are more complex than time will allow to discuss. So if we look at this tree on the left, let's imagine that the green boxes are the level of granularity a sliding window approach gives us. So we can attribute the first box, the second box, the third box, and the fourth box. Notice there's a slight overlap, in this case, between the second and third box of one of the higher level nodes. But let's say what we're interested in, really, are the purple boxes. These are the parts that some malicious person changed to create an exploit in this code. Maybe we identify that author as the author of the first box, or maybe we miss it altogether. Either way, we lose information. But it can get worse. What if the changes are these blocks? Again, maybe we identify one of these sections. No matter what happens, we're losing a lot of information about the authorship of this program. If we just use the sliding window approach. All right. So what are the exact differences between this work and multi-chi? So some of the differences are in terms of the actual method itself. Multi-chi segments at the level of lines of code using features from Word to Vec, which gives a deep learning representation of the text of the code. In this work, we segment at the level of abstract syntax tree nodes and subtrees using features derived from the abstract syntax tree. Other features are in terms of evaluation procedure. Multi-chi was evaluated in the closed world. This work is evaluated in the open world. That means in multi-chi, they assume they knew all the people who could possibly be the author of a segment. In our work, we assume we know some of the possible authors, but there's also other people in the world it could be. Right. Multi-chi had a single set of 562 suspects. In our work, for each project, we look at the authors, the known authors of that project, plus an additional class to represent anyone else. Finally, we look at what we were actually segmenting and how we were building our training set. In multi-chi, they were segmenting individual files, and their train test split was a random selection of files. This is a normal procedure. We did this in Git Blame Who, and it makes up for the fact that it's very difficult to build training sets for authors in the wild. However, this does allow for the possibility that related files could be split between the training and test set. So in this work, we took on the burden of more difficult to build training sets and more authors we could not build training sets for in order to give us the situation in which we are certain that all related files within a project are in either the test or the training. Because at any given time, we test on one project and train on all the other projects. So the fact that we were able to come up with a table with this many differences should be enough to tell us this is not quite a solved problem, although multi-chi was a great start. There's just some unanswered questions left. So to prepare our data, we start by extracting the abstract syntax tree. We assign ground truth to nodes, although I'll note there are issues with that. All right, our ground truth is really at the level of lines, not at AST nodes. And in order to do this assignment, we had to be able to sort of reverse engineer the parsing to link back nodes to the lines from which they originated. And this is just a simple fact of the tools that are available for parsing and for identifying authors of these projects. We then proceed to extract the features. So you can see in this table, on average, each data sample, which is each subtree, had an average of 11 non-zero features and 210 zero-valued features. This would range wildly from leaf nodes, which would have very few non-zero features, to root nodes, which would have many. I'll note that there are no word features, no textual features used except for keywords, which are preserved during parsing. These keywords are the language reserved words. The code was all C++ code, so that's C++ reserved keywords. Things like for, while, things like and. Any words that have special meaning in C++. All of our other features are AST based, including things like count the types of nodes, average depths of types of nodes in the tree, counts of node bigrams, that's pairs, parent-child nodes, maximum and average breadth and depth of the subtree, sibling bigrams and trigrams of the same type. So that's If we have a node that is compound expression and its immediate sibling is a compound expression, that's a sibling bigram. We then remove unique features and constant features. So we use a random forest with 100 trees and a maximum depth of 50. This serves as our baseline. We then use techniques we call adjustment and blocking adjustment that I'll describe briefly now. More details can be found in the paper. So for adjustment, we start by applying our base learner. And then for each subtree, we observe the results from the parent, unless it's the root, and all the children, unless it's the leaf. And then we adjust the results for our subtree with weighted contributions of the parent and children. The intuition is that related subtrees are usually, but not always, by the same author. And the individual subtrees have low information. So we're using the structure of the code of the tree to give us more accurate attributions. Blocking is a little bit different. First, we set a threshold to determine if an author is the same or different between parent and child nodes. If we think they're the same, we combine them into a block. Then, once we've completed our blocking, we average the confidence distributions across each member of a block. We expect higher level blocks, higher level nodes in the block to be more accurate and more confident. And that this will then allow us to get a better attribution for the whole block. We can apply a penalty to having the same class between adjacent blocks because we believe that this is where a change occurs. So we can parameterize this with the threshold and the penalty. In many ways, this is more strict than adjustment. Adjustment allows neighboring nodes to have different authors, but allows them to influence each other. Blocking assumes we know exactly where the changes happen, so the whole block is attributed together. So finally, there's blocking adjustment. We start by blocking, but then we do adjustment with some modifications. Specifically, we use the original distributions to compute parent and child contributions and a contribution from this node itself. This allows us to get the benefits of blocking, but then still have some room for maybe we weren't quite right about where these changes occur. So we had 155 projects from GitHub. So each project is an experiment. It has an open world class and classes for all the programmers of that project that had training data. We had a validation set and a test set. We also created a subset of our validation set that would allow us better control over the amount of training data because it ranged wildly between authors. Some had very little, some had a large amount. So we created this subset where we could really control how much training data we had. So blocking, and therefore blocking adjustment, depend on being able to detect changes in authorship. So most subtrees have the same author as their parent. And these graphs, which are mirrors of each other, show us that we can achieve approximately 85% accuracy detecting changes in authorship with thresholding. Note, we could trivially get very high accuracy by saying it's always the same, but that doesn't actually tell us anything useful. So our results show us that blocking is very strong and that adding adjustment allows some fine tuning. So that's why for overall accuracy, we do our best with blocking adjustment. Although for product average and balanced accuracy, which are both always much higher, we do better with just blocking. We also can observe that some projects are complete failures. We get 0% accuracy, or very close to it. Well, for others, are trivial to say that we can get 100% accuracy, or very close to it. If we are able to get further research into this, it may enhance our understanding of this problem and these techniques. And we'll also demonstrate quickly the test set results in line with what we saw from the validation set. One thing we noticed was that unlike in the get blame who work we did a few years ago, classification confidence is not particularly useful in identifying whether an attribution was correct, except that if we are extremely confident, we were more likely to actually be wrong in this case. We also looked at a combined method where we use blocking adjustment for subtrees that are very small with a very slight change in parameters, and then adjustment for larger subtrees, which gave us higher accuracy in both our validation and test sets. I'll note that research suggests there's an average of 7 nodes per line of code. So between 1 and 35 AST nodes is up to 5 lines of code. And we see that accuracy is correlated with subtree size. And I'll note while there's other issues involved, such as suspect set size, the training on files or projects, our validation set accuracy is comparable to multi-chi at similar size. Okay? And they saw around 90 to 95% accuracy once they got to 5 to 7 nodes. And we were right in that range. 5 to 7 lines of code, which is 35 to 49 nodes. But in this work, we can also then look at smaller, and it's less accurate, but we can still gain some insights from that. So we can do over 80% accuracy in identifying change in authorship, but the data strongly favors same authorship. We also obtained accuracy over 80% for subtrees of at least 25 nodes, around 3.5 lines of code, and over 90% for at least 33 nodes, about 5 lines of code, and 70% for around 5 lines of code in the test set. Test set had lower accuracy for validation than validation for large subtrees, but higher for small. We also saw we can combine our techniques to get a best of all worlds approach. Finally, we see that data is a challenge. We're limited to line level ground truth for a method that's capable of greater granularity. And so maybe we want to parse it with authorship tagging. Also, past work is split by file instead of by project because the lack of data makes this almost necessary. But it opens the possibility we're overestimating our results. We wanted to get towards with this work. We still need to enhance accuracy for the small subtrees. Currently, for leaf nodes, we can get up to about 40% to 50% accuracy. So I'd like to thank the IME Research Lab, DARPA, and Dr. Richard Harang for inspiration several years back that led eventually to this work. So with that, I'd like to thank you